Hi students, welcome to my lectures on chemical reaction engineering. In today's lecture, we are going to discuss about finding the concentrations of all the components in a reaction. Example, if there are, suppose A plus B gives rise to C plus D. What is the concentration of A, B, C, D before the reaction, and what is the concentration of A, B, C, D after the reaction? And that concentrations of A reactants and products depends on how much the reaction has happened. That means, if you know, let us say 10% conversion happened, depending on that, what is your initial amount and what is your final amount. If the conversion is 50%, what is the initial concentrations or moles and what is the final concentration or moles. Okay. Then if we want to find out, we need to follow certain stoichiometry of the reaction. So, in today's lecture, what we do is, we take a certain reactor in which both reactants as well as products present. Suppose the reactor which is having all the 4 components, 2 reactants and 2 products, after certain amount of reaction, what are the concentrations of reactants and what are the concentrations of the products. Certain amount of reaction means after certain conversion, let us say 10% conversion, 20% conversion, and we are going to discuss that stoichiometry behind the finding the concentrations. And at the end of the lecture, we are going to do one small example and applying all the equations we have learned in following the stoichiometry. Let us take a reaction. A moles of A plus B moles of B gives rise to C moles of C plus D moles of D. And always we have to compare with that of per mole of limiting reactant, how much reaction happened. I mean, normally this is the general nomenclature. Okay. Assuming, I mean, I have explained what is the limiting reactant. So, in this also the limiting reactant is A, that means the one which is in less amount. So, always make sure that we are trying to compare per 1 mole of A how much amount of B will consume and how much amount of C will form and how much amount of D will form. From this stoichiometry, every 1 mole of A getting reacted, B by A moles of B will react, C by A moles of C will form, D by A moles of D will form. Okay. That is what the scenario. This is the equation and these are the 4 components A, B, C, D. Among this A, B, C, D, A, B are the reactants, C, D are the products. A and B will consume, C and D will form. Okay, imagine this is the reactor, a certain batch reactor. I mean, this is the molecules of A, molecules of B, molecules of C, molecules of D and molecules of inerts before the reaction. Always, because C and D will be present before the reaction also, because not always the pure mixture coming to the reactor. Sometimes few product molecules will come, few inert molecules will come along with the reactants. So, that is why before the start of the reaction, A is present, B is present, small amount of C is present, small amount of D and inert gas. Generally, people will pump inert gas to control the reaction also. Okay, because if you pump in pure reactants without diluting it, sometimes the reaction will, if it is exothermic, the excessive heat production takes place. In such cases, people send some inert molecules also along with the reactants. Okay, that is a different part. So, currently their molecules of A is present, B is present, C, D and inerts. After the reaction, C will be presenting, D will be present and A is present, B is present, because after the reaction A and B also will present, because not every time complete reaction happens. So, we can expect on the product side after the reaction, along with the product C and D, A and B will also be present. Inert molecules, because inert will not participate in the reaction, so inert will be present and moles of inert will be the same before and after the reaction. Okay. This is before the reaction. Let us denote the symbols. Initial amount of A is Na0, initial amount of B is Nb0, initial amount of C Nc0, initial amount of D Nd0, initial moles of inert is Ni0. After the reaction, that is certain amounts of A is present, remained because some moles of A will not get react, right? Some moles of B will not get reacted. So some amount of B will present after the reaction also. So Na is, remained, moles of A remained after the reaction, and B, moles of B remained after the reaction, and C, moles of C, after the reaction has been formed, D, total amount of D that is present after the reaction, and I, this is moles of I. So all the, after the reaction, if you summate all the moles of A, B, C, D and I, it become total final moles after the reaction. And if you summate all the initial moles of A, B, C, D and I, it become total initial moles NT0. This is NT. Okay, this is a typical nomenclature. So let us think there is some reaction happened. Na, that means our objective is to find out NT0 we know. Na, Nb, Nc, Nd, Ni, these are the terms we have to find out. Because after the reaction, our objective is to find Na, Nb, Nc, Nd, Nt after the reaction. Na, moles of A remained, that is nothing but, if you follow my earlier lecture, you will get to know the things. Initial moles of A minus moles of A reacted. Initial moles of A is Na0, moles of A reacted is minus Na0 into X. X is the conversion. It is after 30% conversion, 40% conversion, 50%. What is the conversion? You can use this formula. How this formula has come? It is there in my earlier lecture. Okay, that means if you common out Na0, that means Na is nothing but, if you common out Na0 from this equation, it is nothing but phi A minus X. What is the phi A? Phi A is nothing but Na0 by Na0, because there is certain nomenclature we will follow. Na by 0 by Na0, Na equal to 1, you get, again you will get back this equation. Okay, Na equal to Na0 into phi A minus X. Similarly, Nb is amount of moles of B remained after the reaction. Nothing but initial moles of B minus moles of B reacted. Initial moles of B is Nb0, moles of B that is reacted. We know how much amount of moles of A reacted is Na0 into X. How much amount of moles of B reacted means, that is why this equation comes in play. Every 1 mole of A, B by A moles of B will form. That means we can relate how much amount of A it is getting reacted means Na0 into X. If A is reacting this much, B will be reacting is B by A times A reacted. That is why Nb0 means initial moles of B minus moles of B reacted. Reacted is B by A into Na0 into X. Therefore, Mb is equal to, if you common out in both the things, Na0, if you common out, then the equation becomes Na0 into phi B minus B by A into X. Phi B is nothing but Nb0 by Na0. Similarly, moles of C formed. Initial moles of C plus C for the reactants, then minus symbol will come. For the products, the plus symbol will come. Because C is getting formed, A and B are getting reacted. So initial moles of C plus moles of C formed during the reaction. That's what this initial moles plus the moles of C that is formed because of the reaction. NC0, the initial moles, plus C by A times Na0 into X. Why the C by A comes? Because every 1 mole of A, C by A moles of C will form. So if this is the amount of A that is getting reacted, that means C by A times this one of moles C will form. Okay, Nc, therefore Nc, if you common out Na from this equation, Na0 into phi C minus C by A times X. What is this phi C? Nc0 by Na0. Similarly, if you do it for 4, moles of D formed, initial moles of D plus moles of D formed. That means initial moles plus moles of D formed. And D0, initial moles of plus D by A into Na0 into X. Why this D by A? Every 1 mole of A is getting reacted, D by A moles of D getting formed. Because this is the amount of A that got reacted, D by A times of this much of D that is going to form. So that is why Nd is equal to Na0 times phi D plus D by A times, where phi D is equal to Nd by Na0. And if there is inerts in the system, and is the moles of I remained, which is equal to initial mole, because inerts are not getting formed. So whatever is there is the initial inerts, that is same moles of B inert will be remained in the reactor. That is, therefore Nd, I mean sorry, this is Ni, okay, is nothing but Ni, which is nothing but Ni is equal to Na0 into phi I. What is phi I? Ni0 by Na0, okay, because anyway Na0 declines, Ni become Ni0. That means final moles of inerts is equal to initial moles of inerts. Okay, now you have identified Na, Nb, Nc, Nd. This amount of A will remain after the reaction, B will remain after C and D and inerts. Now let us form a stoichiometry table. How many species are involved in this particular reaction? In the reactor A, B, C, D, I. What is the initial moles? Na0, Nb0, Nc0, Nd0 and I0. If you summate Na0, Nb0, Nc0, Nd0 and I0, that becomes Nt0, that is total moles present before the reaction. Okay, I know Na from this, Na0 into 1 minus x, Nb equal to Na0 into phi b minus b by a into x, Nc, Nd and Ni. Okay, if you summate, what is the total moles after the reaction? Na plus Nb plus Nc plus Nd plus Ni. These are the amount of moles that is present after the reaction. Then if you summate all, Nt is equal to Nt0, because once you club all the things and if you divide few expressions, then the equation will become Nt0 plus, Nt0 is nothing but Na0, Nb0, Nc0, Nd0, Ni0, if you, all the things will come. Therefore Nt final moles, Nt is initial moles plus D by A plus C by A minus B by A minus 1. What is this? The difference in the D by A product stoichiometry minus reactants stoichiometry. That is D by A plus C by A is the product, minus B by A minus 1 is the reactant, into Na0 into x. Now you can easily find out how much amount of moles that is remained before and after the reaction. What is delta? This is called difference in the stoichiometry. If delta is positive, example, I will go through the example, you will understand. Now let us do a small example and find out what is going to happen. Okay. Let example 2 moles of A plus 4 moles of A gives us 2 moles of C plus 1 mole of D. This is the reaction that is happening in the reactor. Initially I have kept moles of A is 20, initial moles of B is 50, initial moles of C is 2, initial moles of D and D0 is 1. Find Na, Nb, Nc, Nd. Okay, if you do that, and delta, when you have to suppose to do example, in this reactor 50% reaction happened. After this 50% reaction, how you are going to calculate? Let us do the stoichiometry table here like the way we have done, and component A, B, C, D. Initial moles of A is 20, initial moles of B is 50, initial moles of C is 2, initial moles of D is 1. Okay. Now what is phi I? Means phi A, phi B, phi C, phi D. You have to get the values of that is, then only you can able to use this expression to calculate Na, Nb, Nc, Nd. So phi A obviously, which is equal to 1, Na0 by Na0. Phi B means Nb0 by Na0, phi C Nc0 by Na0, phi D Nd0 by Na0, phi I Ni0 by Na0. And everything, because in this example inerts is not present, so you don't need to worry about the inerts. Nb0 by Na0, you get 5 by 2, phi C 1 by 10, phi D 1 by 20. Okay. Then remaining means this one, Na is equal to Na0 into 1 minus x, Nb is equal to Na0 into phi b minus b by a into x. So if you do that, Na0 into 1 minus x after 50% conversion means x is equal to 0.5. Similarly, Nb is equal to Na0 into phi b minus b by a into x. Nc is equal to Na0 plus c by a plus phi c into c by a into 0.5. Nd, See, for the reactants you get the minus symbol, for the products you get the positive symbol. Then what happens is, now if you sum it, what is the total moles remaining after the reaction? How many moles of A that remain in the reaction, how many moles of B remain in the reaction, how many moles of C that has been formed in the reaction, how many moles of D that has formed in the reaction. If you sum it, Na plus Nb plus Nc plus Nd, you get Nt. That means after 50% reaction, you have total moles you have started with 73, and finally after 50% conversion in the reactor only 58 moles is present. Why? Why this initial moles is higher, final moles is lower, is because of the reaction. See, total initial moles is 2A plus 4B, that means total 6 moles of reactant is there, and 2 plus 1, that means on the product side only 3 moles. That means always 6 moles are getting reacted, 3 moles are getting formed. Because of this, the initial moles will be higher before the reaction and the final moles will be lower after the reaction. Whatever the data we have generated here, that is for the 50% conversion, because if the conversion is more, even the moles, there is a more diminishing of the moles will be seen. So you can do it as a homework kind of. I have done it for 50% conversion, you have done it, you can do it for 10%, 20%, 30%. See how my initial moles are there and final moles are there for every conversions. And delta I told you, difference in the stoichiometry. Okay, example this stoichiometry ratio of the products minus, stoichiometry of the product minus stoichiometry of the reactants. So 1 by 2 plus 2 by 2 minus 4 by 2 minus 1. As long as this delta is negative, means you always see more moles in the reactant side, less more, before the reaction more moles will be there, and after the reaction less moles will be there. When this delta is 0, that means initial moles before the reaction will be the same, final moles after the reaction will be the same. Delta is positive, initial moles before the reaction is lower, final moles after the reaction will be higher. So delta has a very important role to play while we are designing the reactors, because it affects the volume significantly. When it affects the volume significantly, and we have to take care of these expansions in the volumes into consideration in designing the reactor. Okay, hope you have learned something about the stoichiometry of the reaction. We will meet up with a new lecture. Thank you very much.